Jehangir Bhabha. At the outset, I thank Professor Sreerup Raychaudhuri for readily agreeing to deliver this special webinar. And like all of you, I keenly look forward to his lecture, and I will not take more time. I will request my colleague, Professor P.D. Nayak, Dean HBNI, to introduce him. Before that, I just want to say a few words. First, I want to also thank the Indian Youth Nuclear Society for coming forward to webcast this program to all its members and contacts. And I also welcome the President and all members of IYNS. Well, Dr. Homi Bhabha was not only a great scientist, but he was also a champion of indigenous development of science and technology. I should say that our university is really blessed to have his name, and we are striving hard to live up to that name, to create high quality human resources for the country, to take forward the department's programs in using nuclear energy, radioactivity, radiation, etc. as tools for the benefit of the society and advancement of the country. When we talk of Dr. Homi Bhabha, usually we discuss his pioneering contributions in the development of nuclear energy in the country, setting up of DAE and its institutions with a visionary approach, etc. But not often we discuss his own pioneering contributions to science through his own research. And today's talk, I hope, will serve to highlight Dr. Homi Bhabha's contributions to physics research, in addition to providing a historical perspective on the science scene when he entered research and the way he made a great impact through his original ideas and research. So I once again thank Professor Sreerup Raychaudhuri for agreeing to deliver this talk. I request Professor P.D. Nayak to briefly introduce Professor Raychaudhuri for the benefit of those of our viewers who may not have interacted with him. Professor Nayak, please.
Thank you, Professor P.R. Vasudev Rao. Good afternoon and welcome to today's webinar to celebrate 111th birth anniversary of our beloved visionary scientist and founder of Professor Homi Jehangir Bhabha. HBN is thankful to today's speaker, Professor Sreerup Raychaudhuri, for accepting our invitations to deliver the talk titled Homi Bhabha and the Early Days of Particle Physics in India. Coming to Professor Sreerup Raychaudhuri, as most of you know, he is a high energy physicist. He obtained his bachelor degree from Presidential College, Calcutta in 1983. Master of Science and PhD from University of Calcutta in the year 1986 and 1994, respectively. He was associated with the SINP, CERN, IIT Kanpur, and presently is professor at Tata Institute of Fundamental Research. His research interests are the physics of elementary particles and fundamental interactions. He is working in the areas of electroweak interactions, supersymmetric models, and theories with extra space-time dimensions. His research work is centered around predicting experimental signatures for theories, especially in the context of high-energy colliding beam machines. Apart from this, he is also interested in high energy. He is also interested in phenomena of favor mixing. In fact, his workplace is a classic example of the amalgamation of input from theoretical ideas, experimental data, and numerical computations. In addition to numerous publications in journals, conferences, and books, he has published many articles on popular science and the history of science. With this brief introductions, I am passing on this platform to Professor Sreerup Raychaudhuri and request him to deliver his talk. Professor Sreerup Raychaudhuri, please.
Thank you, Professor. I'll just share my screen first. Allowed? Is my screen coming? Ah, is it visible? The screen?
Yes,
Yes, yes.
it is
Yes.
visible.
Okay. So thank you, Professor Naik, and thank you, Professor Vasudeva, for this very warm introduction. It is not just a pleasure, but a great honor to be giving this talk, especially because it is in honor of our founder and a great scientist of Son of India, Dr. Homi Bhabha. And I like to say two things before I start this talk. One is that, of course, Dr. Bhabha was a person of such amazing talents and such a range of interests and caliber that anybody who gives a talk on him is about like the story of the blind man and the elephant. So we see one aspect of him and do not realize about the others. So I will be in that position. I will be one of those blind men. I will talk about his contributions to particle physics and to cosmic ray physics. And that's the sort of area in which I can claim to have some understanding. But of course, his enormous contributions to nation building, to nuclear physics, to nuclear energy, to other things like art and to nation, then there were so many aspects of the man, but of course, we cannot cover all of it. What I will try to cover instead is to talk about how particle physics started in India in a small way, and then it grew, and it will just keep on growing. And I will also mention Dr. Bhabha's role in that, and perhaps it will be a little disproportionate contribution of Dr. Bhabha, but after all, it is his 111th birthday, and that's the reason to put it like that. The other thing I like to say is that I'm very happy to see of some old friends, and in particular, my own PhD supervisor, Professor Amitabh Raychaudhuri, I see has joined this. So thank you, Amitabh, for joining this. And of course, whatever I will say, all these things I have learned from you. So I'd like to pay that tribute also to my guru. I don't know, somehow this full screen seems to be going away. Okay. So let me begin by talking about the year 1900, which is when my story starts, from the 1890s to 1900. And at this time, if you remember, that India was a part of the British Empire, and that British Empire spread across the world. Their proud boast was that the sun never set on the British Empire, and all these dark shaded regions in this map are the British Empire. Now, those were the days when if you wanted to do higher studies from India, there were no postgraduate studies in India. If you wanted to do higher studies, you had to go to England. And to do that, you had to come to Bombay and take a ship, which would take you from Karachi and then to Aden, through Aden, to the Red Sea, through the Suez Canal, and out into the Mediterranean, and through the Mediterranean, out through the Straits of Gibraltar. Oh, sorry, this. Sorry. This keeps disappearing. I don't know what to do. Okay. It's a problem. I don't know. Somehow the. Okay, so I've already shown you this. And of course, today it's possible just to take a flight in maybe some 8 or 9 hours and reach there. But remember that all the difficulties of that long sea voyage were part of the difficulties of doing science. Okay, so let me just say that the science, of course, we are talking about started from the other end of this long line. And my story starts with the discovery of radioactivity, where in 1896, Becquerel stumbled upon the fact that uranium salts can affect photographic plates. Within 2 years, Gerhard Schmidt and Marie Curie had discovered, it's a phenomenon I've never seen before. New phenomenon. Discovered that thorium also affects photographic plates. Then Pierre and Marie Curie discovered polonium and radium, and Marie Curie coined the name radioactivity. 1898. In 1899, Rutherford discovered alpha and beta rays and invented the concept of half-life, which is so crucial to the study of nuclear physics. 1900, Paul Villard discovered highly penetrating radiation, which we now call gamma rays. 1902, Rutherford and Soddy suggested that radioactivity involves the disintegration of atoms. In 1907, Rutherford and his student Thomas Royds proved that alpha rays are just doubly ionized helium atoms, and that established the fact that atoms were indeed breaking up. In 1913, Soddy and Fahans from Manchester discovered the radioactive displacement law. And finally, in 1917, Soddy and his student Ada Hitchens discovered the existence of isotopes. I couldn't find a photograph of Ada Hitchens on the internet, so I'm showing you just her silhouette, and that will be true for a few other people also. Well, radioactivity research also started in India very early, and surprisingly, it was in Bombay and from the St. Xavier's College. There were two Jesuit fathers. Again, I couldn't find their pictures, so I show you this some cartoon. Father Adolphus Steichen and Father Heinrich Schell. They were both of them were graduates from Göttingen University, and one was the professor of physics and one was the professor of chemistry. And what they did is that at that time it was important, people were studying radioactivity in hot springs. So they went to Tua, which is near Baroda, and to study that radioactivity. Now, some time before, Professor Ramsay from Indiana University, I can only show you this very hazy picture of him. He had claimed that the radioactivity of hot springs increases with the flow of water and decreases when it falls, basically, which means that the radioactivity was a property of the water. But Father Steichen's paper states that he and Father Schell found the exact opposite. And they correctly attributed it to the fact that some radioactive material, which was solid, was being washed out by the spring. So when there was more water, it was dilute, and therefore you saw less radioactivity. Now notice that the work was done between around 1910, but the paper didn't come out till 6 years after. And the reason was that during the First World War, which broke out in 1914, both these German fathers were interned and put in a camp as enemy aliens because they were still German citizens and the First World War had broken out, and hence the delay came in publishing the paper. Later, Father Steichen carried out a study of the hot springs in the Madras Presidency, and this was a 5-year project. And to just give you an idea of the kind of value of the rupee in those days, he was given a grant of 1,000 rupees for this. Okay. At the same time, a young professor in the IISc, Herbert Watson, he decided that he should study the radioactivity in the rocks around the Kolar township and gold mines. So if Bangalore is here, then the Kolar is here and the mines are around here. We'll come back to the story of Kolar later. But these are some of the oldest rocks in the Earth's crust, and the gold mines go more than 4 kilometers down, so they could look at those samples. And his assistants in this were Goshta Bihari Pal, who was a student, and W.F.S. Smith, who was working in the Mysore Geological Department. No photographs are available, but they didn't find any radioactivity in these rocks. And this has an important thing when I will come to the story of Kolar later. The negative result was published first in the Proceedings of the Indian Academy of Sciences, 1914, and then in the Philosophical Magazine, which was then one of the top journals. And then 1916, Watson left India and went back to the University of London. More developments in nuclear physics took place over the next 2 decades. I'll just go through them very quickly. Between 1908 to 1910, Geiger and Marsden studied the alpha particle scattering from gold atoms, famous gold foil experiment. They collected all the data, and Rutherford proved that this data can be explained only if the positive charge of the atom resides in a tiny fraction right inside, and he called this the nucleus. And it follows that the hydrogen nucleus, which is the lightest nucleus, must be an elementary particle, the proton. So now you have two elementary particles, the electron, which has been discovered by Thomson, and the proton. In 1930, Niels Bohr explained the atomic line spectra using the new quantum theory. Henry Moseley, at the same time, proved that the charge on the nucleus is equal to the atomic number. Very nice work by this young scientist who died in the First World War. In 1920, Rutherford, who by then was in Cambridge, he predicted that there should be something called the neutron, but then again he went back and said, I'm not sure. However, by 1931, when quantum mechanics had come, it was possible for Dmitry Ivanenko, not a very well-known name, who predicted that the neutron has to exist. There has to be something like the neutron inside the nucleus if you are to understand the beta decay spectrum. And in 1932, within a year, James Chadwick had discovered the neutron. Let's come back to India, and I have to show you this iconic picture, which shows you all the greats of the Calcutta School of Physics at that time, led by Professor famous Acharya J.C. Bose, with other luminaries like Meghnad Saha, J.C. Ghosh, S.N. Bose. But the person I'm going to focus on is D.M. Bose. Sir Devendra Mohan Bose, who was actually the nephew of the Acharya. And here we see a younger portrait of him. And he is well known as D.M. Bose. So, in 1907, Bose sailed to England and he enrolled in the Christ College, Cambridge. You see the college here. And there he had some very famous teachers. He had J.J. Thomson, the discoverer of the electron, and C.T.R. Wilson, who created the cloud chamber. So I show you a picture here of the actual cloud chamber. This is in the Cambridge Cavendish Museum, which is what was built by Wilson himself. And here is one of the first photographs of an alpha decay taken by Wilson, a very hazy cloud chamber photograph. So both these scientists were, of course, Nobel laureates, and it was they who inspired him, but it was more Wilson than Thomson, because he really learned how to make a cloud chamber. It was the state-of-the-art science in those days. So in 1913, D.M. Bose returned to India. He joined the City College as a lecturer. But then 1 year later, when the new department of physics was opened at the University of Calcutta, it was a postgraduate department, he was appointed as the Sir Rashbihari Ghosh Professor of Physics. So Sir Ashutosh Mukherjee, the famous mathematician and jurist, he was the first Indian Vice Chancellor of Calcutta University who founded the postgraduate science department. And he was able to persuade his friend, Sir Rashbihari Ghosh, who was an eminent lawyer, to donate more than 21 lakh of rupees to Calcutta University for this purpose. So at the present rate of exchange, this is something like about rupees 270 crores. So I really wish we had individual donors who are so generous today. In 1914, when Bose joined the Ghosh professorship, he found that it came with a Ghosh traveling fellowship, which he was supposed to visit a foreign country and learn something for 2 years. And Bose immediately decided to make a visit to the laboratory of Erich Wegener in Berlin. Now, why Erich Wegener? Because Erich Wegener was a professor at the Berlin Agricultural University, but from his laboratory, came a stream of precise measurements of cosmic rays. So cosmic rays had been discovered only in 1912. So within 2 years, the fact that Bose wanted to go there showed his early interest in cosmic rays and the fact that he was very much up with the times. So we have this testimony from Bruno Rossi, the Nobel laureate, that the measurements made by Erich Wegener and his group were brought to an unprecedented degree of precision. But hardly had he was settled down in Germany when the First World War broke out. Now, whatever had happened to the Germans' fathers in India, the opposite happened to Bose, because he was an enemy alien now in Germany. But the Germans did not put him in a camp. He was not interned. He was only required to report regularly to the police. he was allowed to carry out his research work. And he actually made very good use of this time. What he did was he successfully built a cloud chamber and he managed to record the recoil tracks of protons produced by fast alpha particles. So this was the first time these H particles, these hydrogen ions, had been seen experimentally. And it also proved that momentum is conserved at the atomic scale. This was later used by Compton to explain the photon-electron scattering. But this was the first observation that, in fact, momentum conservation does hold at the atomic scale. In 1919, Bose was awarded a PhD by the University of Berlin for this work, and part of this work had been published in 1916. But Bose also made use of the time to attend the famous lectures given by Max Planck at the Kaiser Wilhelm Institute in Berlin. And he wrote that after attending Planck's lectures, I learned what a system of physics meant in which the whole subject was developed from a unitary standpoint and with a minimum assumptions. So he certainly liked the lectures. Not everybody who attended the lectures liked them. So here is a comment from Rudolf Piles, who says, Planck's lectures were among the worst I ever attended. So you can't please everybody. Well, let's come back. In 1919, when the First World War was over, Bose returned to Kolkata to resume his position as Raspberry Ghosh professor. But now he had a colleague of great eminence, and that was the Sir Taraknath Palit Professor of Physics, Palit Professor C.V. Raman, who was originally a civil servant in the Audit and Account Service. In 1917, he had been persuaded by Sir Ashutosh to abandon his government job and take up an academic position at half the salary. But he was so dedicated to science, he was willing to forego half his salary and come and do academics. And there were other bright sparks in the Calcutta University Physics Department, very famous people, S.K. Mitra, founder of radiophysics in India, S.N. Bose, who statistics, B.B. Roy, the famous spectroscopist, and M.N. Saha, founder of Saha Institute and Saha ionization formula. But coming back to Bose, he immediately started publishing papers in Nature, and he was looking at tracks of alpha particles in helium, cloud chamber photographs, and he was working with his student S.K. Ghosh, Subodh Kumar Ghosh. Again, I couldn't find a picture, but he was the collaborator. But it was not only in Kolkata. In Jaipur, the Maharaja's College had a professor called N.F. Soonawala who wrote this paper in Indian Journal of Physics. He had this interesting suggestion that all nuclei are made up of electrons, protons, and noble gas nuclei. So if you replace the noble gas nuclei by neutrons, you're almost dead. In fact, what he had in his paper was an early version of what we call the Aufbau principle, which was later used by Niels Bohr to set up the periodic table. There was A.C. Banerjee, who had passed this very difficult exam from Cambridge called the Tripos, and he was called the Wrangler, if you did that. And he joined the Allahabad University and was the first Indian to apply in collaboration with Meghnad Saha, who had moved there to Allahabad University for some time. They were the first Indians to apply quantum mechanics to the study of nuclear spectroscopy. There was also B.M. Sen. He was also a wrangler from Cambridge. He wrote in Nature in the Philosophical Magazine on beta rays. And he was one of the first. He had originally joined Rajshahi College. Later, he became principal of Presidency College. And he tried to explain the spectral features of beta, the decay, proving that the neutron, among the ways, is for Dirac fermion. This is the original paper which proved this. Today, we take it for granted. But the first paper, which I could really call a particle physics paper, was written again from Allahabad, but it was written by Meghnad Saha with his master's student, D.S. Kothari. And Kothari had a MSc project to do, and Saha gave him the project of trying to explain the continuous energy distribution of the beta rays emitted from a radioactive nucleus. So we know, of course, that in the beta decay, a neutron decays to a proton and an electron. But if it was only that, then you would have a constant, a fixed energy for the emerging beta ray electron. So what Saha and Kothari suggested is that every beta ray process is not actually a decay of an electron coming out from the nucleus, but basically if you have a nucleus, it's a gamma ray which comes out. And then in the, sorry, again. So it's a gamma ray which comes out from the nucleus, and in the field of the nucleus, it immediately does a pair creation of an electron and a positron. And then one of them is absorbed in the nucleus, the other comes out. So when you see the particle coming out, that's not the original particle which came from the nucleus. Now this is a beautiful idea. And see, because the excess momentum can now be taken up by the nucleus. So you will not have a fixed energy of this emergent beta ray, but a spectrum. So it's an economic way of understanding the continuous beta ray spectrum. And we also know that beta decays are usually followed by gamma decays. So you see the same sample, you see both of them happening. So the Saha-Kothari explanation would be that the beta and gamma rays, some of the gammas did a pair creation, some did not. So you saw both beta and gamma rays from the same sample. And the nice thing is that this theory does not require a neutrino, because at that time people thought a neutrino is some eccentric idea of Pauli's. However, the Fermi theory of beta decay, which came 1 year later in 1934, and then its verification, detailed verification by Curry, it killed the Saha-Kothari theory. So the spectrum you see here is this nicely explained by Fermi theory of beta decay, but the Saha-Kothari theory would give you a continuous spectrum, like this, a continuously falling spectrum. So the theory didn't stand the test of experiment, but it was, I think, a very beautiful theory when it was proposed, and certainly more economical than Pauli's. It's just that nature is not that way. Well, during the 1930s, so Europe was in complete turmoil with the coming of Hitler, Mussolini, Jews being thrown out of Europe, preparations for war, the Great Depression. Now, these did not affect India so much, and in fact, Meghnad Saha at that time developed his theory of monopoles. And in fact, he tried out a theory in which this neutron, which had just been discovered, could be a bound state of two monopoles, which would explain why it has a magnetic dipole moment. Of course, this theory did not last, but we said no, that Saha's derivation of the monopole is more elegant mathematically, but maybe less intuitive than Dirac's. Of course, today we know that the magnetic moment of the neutron is because it has electrically charged components, which are the quarks. There was also K.C. Kerr and his collaborators Ganguly and Mukherjee, who developed an interesting theory of the atomic nucleus, which was based on the idea that there was a hard negative core surrounded by alpha particles. So just like the atom has a nucleus surrounded by electrons, here there was a hard negative core surrounded by alpha particles. And this original idea was Rutherford's. But the Calcutta group actually tried to apply the Schrodinger equation and tried to get the nuclear spectroscopy from this. And it was a bit naive, but in some sense, the spectra they got from this, mostly because of the spherical symmetry and the angular momentum part of the calculation, gave similar results to the nuclear shell model, which is sort of the most popular model today. Of course, today, K.C. Kerr's work has been forgotten, and he is remembered because he opposed Einstein's relativity anyway. Now, on this kind of scenario, Homi Bhabha suddenly appeared like a comet in the sky, and suddenly, for some time, he completely transformed the nature of work by Indians. So let me say something about Bhabha himself. So his full name actually was Homi Jehangir Bhabha, Jehangir being the name of his father. But of course, he always signed himself as Homi Bhabha, and I will continue to refer to him as Dr. Bhabha. So he was a young Parsi boy from a wealthy Bombay family, closely related to the Tata family. And he was actually sent to Cambridge to study mechanical engineering. That is because his father, in consultation with his uncle Sir Dorabji Tata, who was the son of Jamshedji Tata, and at that time head of the Tata Empire, so they actually wanted him to come back to India and take charge of the Tata Iron and Steel plant at Jamshedpur, which had been founded some years back. But as we know, in Cambridge, Bhabha attended lectures by Thomson and then others, and especially Dirac. And this determined him to become a physicist. And he wrote to his father saying, I seriously say to you that business or job as an engineer is not the thing for me. Physics is my line. I shall do great things here. And indeed he did. For each man can do but best in only that thing of which he is passionately fond. So very wise words from a very young man. But he did manage to persuade his father to let him do the mathematical course, which included mathematical physics at Cambridge. But his father stipulated that only after he had qualified in the mechanical course, which he did in 1930. Now, this dual training was to stand him in very good stead later, and that is the part I will not talk about, but the entire setting up of the atomic energy establishment would perhaps have been much more difficult if he had only had training as a physicist or a theoretical scientist. So, this brilliant young Indian at Cambridge was a protege of Dirac, and he spent a total of 9 years in Cambridge and worked, among others, with very famous people: Fowler, who was his former supervisor, Dirac, Pauli, Bohr, Fermi, and most famously Heitler, and I'll come to that. So let me explain the background under in which he did that work. So the background starts with a person, I don't need to tell you who he is. In relativity, unlike classical physics, energy can be both positive and negative. And this is because the energy-momentum relation, if you plot energy versus momentum, the relation is a quadratic relation. So if you want to find the energy, then this is the classical formula, okay? E is p squared by twice m, we know that. So there's no problem there. Energy starts from zero, it's always positive. But in relativity, there are two branches. The energy squared is given by this, so the energy can be either the positive square root or the negative square root. Now, so long as we are in classical physics, no problem. Once you are in this positive branch, you cannot cross over to the negative branch because there is an energy gap which is twice m naught c squared. So you can't cross this because discrete changes are not allowed. So once you're in the positive branch, you can simply say all of nature is in the positive branch. This is not a physical thing. But quantum mechanics is different. Quantum mechanics allows you to make a quantum jump from the positive to the negative side. And this is something which plagues all of relativistic quantum mechanics. So Dirac's 1928 paper on the relativistic quantum theory of the electron included these negative energy states. Now, of course, if that happens, a positive energy electron can jump to the negative energy state and then it will simply go down, increasing momentum as it goes, increasing the magnitude of the energy will keep on increasing. And therefore, an infinite amount of energy will be emitted from this. That's a catastrophic situation. So we can't have that happen. So what Dirac suggested was that maybe this entire negative energy states, they are all filled up by some electrons already. And there's a Pauli exclusion principle which forbids an electron which is here from going there. So this would keep all the electrons in the positive energy states there. And he said somehow these negative energy electrons in the C are invisible. But there is a problem here, and that is that an electron from this negative energy C could also make a quantum jump here. So what would happen is that the electron would suddenly appear here and a sort of hole in the C would appear here, and this would appear like a positron. So he did predict that sometimes you could have positrons if you gave some energy into this vacuum, which is the C. Moreover, identical electrons could get exchanged between positive and negative energies, leading to a totally bizarre concept called Zitterbewegung, in which an electron sort of moves forward and backward, like a jittery motion, like the way I'm moving my cursor. It will move not smoothly. There's a free electron will not move smoothly, but will move forward and backward. So prevent this, one needs to forbid this type of exchange and leads to something called the hole theory, and the modern name for these holes is antiparticles. Now, Bhabha, initially, Dirac's theory was greeted with derision. People didn't take it seriously. People thought he's some crazy theorist. But in 1932, Anderson discovered the positron, the first so-called antiparticle. So it seemed that there was some truth in it. Taking up from this, in 1933, Pauli and Weisskopf invented quantum field theory as a theory not of a particle and its antiparticle, but of a theory which has particles and antiparticles as part of the basic particle content. So now the question arose whether if quantum field theory is correct or not. Is the positron really the antiparticle? Does it correspond to a hole in the sea? Or is it just a different particle which happens by accident to have the same mass and opposite charge? We know, for example, that the proton and neutron have almost the same mass. And one is charged and one is not charged. So could it be that the positron is just a positive particle which happens to have the same mass as the electron? Now, to answer this question, Bhabha was intrigued by positrons from the beginning. So from the time he attended Dirac's lectures, he first set himself to calculate this cross section, did some work on positrons, for electron-positron scattering, and under the two assumptions. One assumption that the positron is the antiparticle, and one is that it's not the antiparticle. And then if these give different results, you could compare them with the data on electron-positron scattering to see which is true. So in fact, his 1936 paper on the scattering of positrons by electrons with exchange on Dirac's theory of the positron was the first calculation of what could be found today in any textbook, and it's called Bhabha scattering. It was one of the foundational works in the newly developing subject of quantum electrodynamics or quantum field theory, quantum electrodynamics, QED. Remember, this was long before the days of Feynman diagrams, so everything had to be done from first principles, which indeed Bhabha did. But I will try to explain the basic idea to you using the idea of Feynman diagrams, which is much simpler. So, suppose the positron is a different particle from the electron, just like the proton, for example. In that case, the positron could scatter from an electron just by exchanging a photon. So the positron remains a positron, the electron remains an electron, but they exchange a photon and therefore their trajectories change. So that's one way the scattering can happen. And if this is all that happens, then the cross-section is like this. Here is what is called the Rutherford factor, and you have a cos 4 sine the 4 theta by 2 dependence, where theta is the scattering angle between the initial and the final state of the electron. Now, if the positron is also the antiparticle of the electron, you can have another diagram where the electron and positron annihilate together to form a photon, and then from the photon and electron and positron pair is created, and you get another diagram like this. So if that happens, so if the positron is a different particle, it cannot annihilate the electron. So therefore, this diagram would not be there. And this diagram gives you these extra contributions, and you see now a cos squared theta contribution, not the cos to the 4 theta contribution. So now if you make a plot, so once again I will not show you the original data that Bhabha used, but I'll use a much more modern data, measurements taken from the Stanford Collider in the 1970s, and you see here a plot of the theoretical calculation of Bhabha scattering using the formula I showed you in the previous slide. And here are the experimental data, and you see that it fits almost perfectly. Now, had we gone with the idea of Bhabha, that to take the other possibility, no annihilation diagram, imagine the positron as a different particle, you would have got a graph which was something like the red graph here, which clearly doesn't fit the data. So, here is a very clear example that Bhabha scattering, indeed, that's the right way to calculate it. But what is important, and this is often forgotten, is that Bhabha's work was the first experimental proof that the positron is indeed an antiparticle, and therefore the quantum field theory, the way of thinking, is the right way. And today we take it for granted, but at that time it was not taken so seriously. And Bhabha was the first piece of work which proved that the positron is an antiparticle. Then, not only did he go ahead with this, but soon on the heels of this followed the Bhabha-Heitler theory of cosmic rays. So a little introduction to Heitler. He was already famous when Bhabha met him, because the Heitler-London theory is the basic theory of the chemical bond. He already had a faculty position in Göttingen, but he was dismissed by Hitler's government because he was a Jew. He sought asylum in England and he got a position in the Wills Laboratory at Bristol. Now, Bhabha and Heitler, so they met on various occasions. Cambridge is not all that far from Bristol, and they were both interested in the same problem. How do high-energy electrons in cosmic rays penetrate the 8 to 10 kilometers of the atmosphere and reach the sea level? Now, why was this a problem? It was because Hans Bethe and Heitler had already calculated how much energy is lost by a high-energy electron in the field when you have multiple nuclei of nitrogen and oxygen, which is what air is. Lots of nitrogen and oxygen nuclei in the air. So they had concluded that there was no way such electrons can go more than 2 kilometers. But yet, we are seeing electrons regularly. If you put a cosmic ray detector on the ground, you will see electrons coming from the top of the atmosphere coming to the ground. So what's going on? How is it possible? So the possibility that this may not be a one-step process, it may not be the same electron, but another electron produced in a cascade, idea was there. It had already been suggested. It was in the air. And Bhabha had heard it from Hugh Carmichael at Cambridge. I could only find this photograph of him. And Heitler had heard it from Lothar Nordheim at Munich. But these were senior physicists, and at that time they didn't take the Bethe-Heitler calculation so seriously, simply because they didn't believe QED was the right theory. So they were very suspicious of QED. But on the other hand, Heitler, of course, had done the calculation, and Bhabha had himself done this important work to prove the usefulness of QED. So they took it seriously, and they showed that if you can have a cascade of particles, which I will explain in a moment, then you can explain the fact that you see electrons at the low energies. And this is the famous paper by Bhabha and Heitler, and you see Bhabha is still in Cambridge, in the Gonville and Keyes College, and Heitler is Bristol. So what is the idea? Idea is a common picture that typically cosmic rays are high energy particles which come from the outside the Earth, mostly hydrogen nuclei, hydrogen ions from the sun, but sometimes more other particles which come from elsewhere in the cosmos. So the idea is that one of those particles comes and hits the atmosphere up and there, and it produces, because it has very high energy, it produces a bunch of other particles. You have E is equal to mc squared. New particles can be created. Those particles themselves have energy, and they come down and create other ones. So therefore, when you see electrons at the lower levels near the ground, what you are seeing are not electrons which have been produced 8 or 10 kilometers above, but maybe somewhere between 1 to 2 kilometers above. They are secondary electrons produced through the shower. And I'll quickly show you. Okay, before I do that, let me mention that the Bhabha-Heitler paper was published in 1936 in the Proceedings of the Royal Society. 1 year later, I mean the days of the archive, where a paper appears and everyone reads it the next day, were not there. So it took time for ideas to propagate. 1 year later, in 1937, Carlson and Oppenheimer published the same results in the Physical Review D, but they were too late. This is known as the Bhabha-Heitler theory and not as the Carlson. So here is a little simulation, a little cartoon of how this thing goes. A high energy particle comes at the top of the atmosphere, hits the nucleus there, and then you get this whole shower of particles which stream out, and this is a cosmic ray shower. So you see at the ground, you see this shower coming from. Now then, if you remember the story of King Midas in Greek mythology, that whatever he touched turned to gold. So you see him here in this cartoon with taking these copper coins and turning them into gold with his touch. So in these periods, Bhabha had that Midas touch. Whatever he wrote on, whatever he touched, it became a very significant result. He touched turned into gold. So in 1936, in those days, the cosmic rays, it looked like there was one hard component which reached the ground and which was able to penetrate more than 10 centimeters of lead, where an electron, maximum electrons can go through 2 or 3 centimeters of lead. So he suggested, by studying that this hard component could be due to a new particle, which would be similar to the electron, but about 100 times more massive. So it was a rough ballpark calculation. And in 1937, within a year, Anderson and Neddermeyer had actually discovered the muon, which is like the electron, just as Bhabha predicted, and it is 200 times instead of 100 times more massive, and it does decay into electrons, which is also something Bhabha had predicted. So in a sense, the muon was predicted by Bhabha, and this is something which is not commonly mentioned in the textbooks. Moreover, there is something which is even more common in the textbooks, but which was actually first proved by Bhabha. Bhabha proved that when cosmic ray muons come from the upper atmosphere, the fact that they have this long lifetime is due to time dilation. And therefore, this actually proved a firm experimental basis for Einstein's theory of relativity. In the days when relativity was under attack, Einstein was under attack, mostly because of the Nazi, the anti-Jewish feeling. But there were a lot of people writing against relativity. And every now and then, of course, somebody comes up with an alternative theory also. But relativity has stood the test of time. And it's interesting that Bhabha gave this. And this is now a textbook exercise. Every MSc or even BSc students do this as an exercise to show that the muons can come from the upper atmosphere. But Bhabha was the first to do it. And then in 1935, Yukawa predicted the pion, which he called the mesotron, which we call the pion today, as a spin-zero particle, spinless particle, which mediates the interactions between spin-half nucleons. In 1937, Bhabha pointed out that when you take two spin half particles, nucleons, you can combine them either to give you a zero spin or a one spin. And this one spin, spin one particle, would be a vector meson. And he had predicted that you would see similar things in nuclei. This was predicted in 1937. These mesons that actually exist, they are called the Rho mesons, and they were discovered only in 1961. So you see that he was so far ahead of his time. Not surprisingly, Bhabha was very highly regarded among the scientists of his time. You see him here with three very, very famous scientists. And if you look carefully at the picture, you will see that it is Bhabha who is doing the talking. The others are listening. All right. So all good things come to an end. So Bhabha, like the Adam and Eve, had to leave Cambridge where he was doing so well. And the reason for that was this gentleman whose face you see. So in summer 1939, Homi Bhabha came home from Cambridge to spend a well-earned vacation with his family. He had not come home for 4 or 5 years. But before he could return, the Second World War broke out, and there was a danger from U-boats or submarines that there would be sinking ships. So only military people were allowed on board ships, civilian passengers were banned. So he just couldn't go back to Cambridge, and it would be 6 years till the war ended before he could visit Cambridge again. So now forced to seek a job in India, Bhabha wrote to various places, and he got 3 offers, one from Allahabad University, one from the Indian Institute for Cultivation of Science, Calcutta, where K.S. Krishnan, who was then the director, tried very hard to get him, and from the IISc Bangalore, where C.V. Raman was the director, and he made him many, many promises and said, please come here, I will give you everything you need. He was not the director then, he was head of the physics. Anyway, once Bhabha agreed to go to Bangalore and join, Raman gave him a couple of rooms and said, okay, you have 2 rooms, now start a cosmic ray group. I think many young scientists, especially experimentalists, will understand the phenomenon. So now for the first time in his life, Homi Bhabha faced the reality of doing science in a colonized country. He had been born in Bombay with a silver spoon in his mouth, educated at the best places. Then he went to Cambridge, worked with the top places, went to Niels Bohr's Institute in Copenhagen, went to work with Pauli at Zurich, and so on. Worked in places where it was much easier. But in Bangalore, none of those facilities existed. But for 6 years, he worked very hard in Bangalore. He tried at the same time to pursue his theoretical ideas, and at the same time, he tried to set up an experimental cosmic ray unit. Now, I have to say, and we'll look at the cause later, none of this theoretical work which he did has the impact of his Cambridge work. We'll come to that. But first, let's see what is the work he did. So during the Bangalore years, we have a picture here of Bhabha in front of this main building of IISc, trying to launch a balloon and send detectors up into the upper atmosphere. So, separating the soft and hard components of cosmic rays, so he invented something called the Bhabha Method, which was to use 2 different layers of absorbing material and interspersed with counters which are in coincidence. These could separate out secondary showers from the primary ones. So this was an innovation, and these are known as Bhabha Counters. So the Bhabha Counters were first carried in aeroplanes at heights of 15,000 feet first, then 30,000 feet, and finally 40,000 feet. And later he developed flight balloons which could stay longer in the upper atmosphere and collect more data. And then comparison with the results obtained at Chicago by Shine, Jesse, and Fuller showed that the hard component of cosmic rays shows no latitude effect, but the soft component does. And this was consistent. It proved Bhabha's early guess that the hard component is mostly muons which don't show the latitude effect, and high energy protons, which Blackett had suggested, but the soft components are electrons which will show a latitude effect, which is due to the Earth's magnetic field. There was also important theoretical work which he carried out, and he wrote this famous paper with Corbin, who was in Cambridge, and these are known as the Bhabha-Corbin equations. So let me just explain that. So Dirac's equation, which I described earlier, it works in a fixed electric field background. It doesn't take into account the effect of radiation reaction, because actually a charged particle will be emitting photons, and they will have some momentum conservation, show some reaction. That's an extra force on the electron. So Dirac was able to develop a theory which did it, but he could do it only for the electron which has spin 0. Bhabha and Corbin were able to generalize this theory to spinning electrons, getting the Bhabha-Corbin equations. Then, further by developing the theory of vector mesons, Bhabha and Heitler found that the theory of their scattering from nucleons can only work if there are also nucleon isobars, which have the same mass but higher spin. And these were actually found by Fermi in 1952. And finally, the initial Bhabha-Heitler theory had ignored energy losses by collisions as a shower developed. Okay, they just assume that the total energy which is there is developing into new particles, but that's not true. There's also a lot of energy lost due to collisions. So this was remedied by Bhabha and his student Chakravarti, who developed, actually it is very mathematically tricky paper, so they developed a convergent series solution to the equation for shower development. So then Bhabha found that the environment was not conducive there, despite the good work he was doing. It was too much hard work. So he wanted to found an institute for himself. And that led, with the help of the Tatas, to the foundation of the Tata Institute of Fundamental Research, where I'm working from. And here you see a picture of the first place where it was done. This was in a bungalow called Kenilworth, which belonged to Bhabha's aunt, who stayed in only one room in this huge bungalow. So she let him use the rest of it for his institute. And of course, today a different building stands there. But it still belongs to DA. Well, what did Bhabha do in the Bombay years? So one of the things that he had built here was a Cockcroft-Walton generator, and we see him here with that. You also see from his body language that here he's very much master of the show and much more confident. Well, so Bhabha and his collaborators, they started, he built up a cosmic and started sending these cosmic ray detectors to the upper atmosphere. This was a continuation of his Bangalore work, and later this work was taken up by M.G. Kemen, and I will talk about the others later. Bhabha also formed a nuclear emulsions group, and I will come to the story of emulsions later. But Bhabha and Daniel first made an airplane flight at 8,000 feet and recorded a meson track among what they did. Later, this work was taken up by Bernard Peters. Bhabha also got a 12-inch diameter cloud chamber built at the TFR, which was used in surface level studies. Later, this work was also taken up by Roy Daniel, and his team also built India's first Cockcroft-Walton generator, which picture I'm showing. During this period, Bhabha also initiated muon measurements of the polar mines, which I will tell you more about. But he was also doing theoretical work. And this paper, the relativistic wave equations for elementary particles, contains what are known as the Bhabha equations. So, generally, a relativistic wave equation has to be linear in the energy momentum. And Dirac's equation does this for spin half particles. Bhabha was able to generalize this to particles of arbitrary spin. Lubansky had done it independently in Poland. So, putting them together, they are known today as the Bhabha-Lubansky equations. The quantum field theory of this was a single particle equations. The quantum field theory of this had to wait to 1979 when it was developed by Weinberg. Bhabha and his student Chakravarti continued to develop the theory of soft showers in absorption plates. And then Bhabha and Alladi Ramakrishnan, whom I will talk about briefly later, also applied stochastic techniques for the first time to shower development. In nuclear-nucleon scattering, the cross-sections are much smaller than would be expected for point particles. Bhabha tried to give an explanation in terms of relativistic contraction of the nucleus and a very short interaction time. This was a nice idea, but the problem was actually solved only in 1968 with Feynman's idea of partons, showing that the nucleons, actually it's not the nucleons which scatter, but the partons, which are components of the nucleons which scatter from each other. So I will now quote Professor Virender Singh's. It's a beautiful article on Bhabha's work in details, which I have heavily depended upon. But his comments I should quote in toto because it's a very beautiful description of how Bhabha's work should be described. He says Bhabha's work in theoretical physics was carried out in a wide variety of styles. His work with Heitler is of a kind which could now be described as phenomenology. Then this was the work which actually got the most importance at that time because it was directly connected with experiments. Some of his work had speculative components, for example, the prediction of the muon, the prediction of nucleon isobars, and of course the rho particle. And of course, these were all proved later. His work on the theory of relativistic spinning particles in classical physics were originally motivated by the problem of radiation reaction. One cannot, however, help feeling that this motivation was strongly reinforced by the aesthetic appeal of this investigation. This is the mark of a theorist. And then his work on relativistically invariant wave equations, though motivated by a possible application to nucleons, as he said, could really be regarded as almost pure mathematical group theory. In fact, his early student and collaborator Harish Chandra later took this ahead and did a lot of work on pure group theory, mathematics. In fact, he became a mathematician. And he says that though Bhabha's main scientific work and achievements were in theoretical physics, he was sensitive to the importance of experimental work as well. His cosmic ray experiments were not carried out using some other people's techniques, but using a novel method devised by himself. So, versatile man, basically a theorist, but also having experimental skills and other skills, which I will not talk about. Well, in 1954, Bhabha set up the atomic energy establishment at Trombay, and from that time onwards, his energy, though he kept abreast with what was going on in particle physics, essentially his interest shifted to nuclear energy and nuclear reactions. You see him with the prototype of the first Apsara reactor. Here, showing the demonstration to people. And from that time, it's a different part of the story. So now I will stop this part and I will move back to the other end of the country briefly. So I am running very slow. So I'll just try to be a little faster on this. So charged particles leave tracks in photographic emulsion. It was discovered by Kinoshita in 1910. But the use of photographic rays to study cosmic rays was pioneered by these two ladies, Marietta Blau and her student Herta Wambacher at the Radium Institute of Vienna. Now, these two women, unfortunately, their work was certainly of Nobel-worthy quality, but they were victims of severe gender and also political discriminations on their lives, and I will tell you a little more about it later. Anyway, the 25th session of the Indian Science Congress was held at Kolkata in 1938, and many important people had come to that. But in the cosmic ray session, there was a lively discussion which was led by Walter Bothe, who later won the Nobel Prize for the coincidence method, and Geoffrey Taylor, who was supposed to be Cambridge's top expert on cosmic rays. And Bothe in particular, he discovered the new photographic emulsion techniques of Blau and Wambacher, that you could use photographic plates to detect cosmic rays instead of cumbersome cloud chambers. And these discussions fell on fertile ground. So D.M. Bose, you remember D.M. Bose? He was still interested in cosmic rays. He had just become director of the Bose Institute, and he had a very bright student called Bhabha Chaudhuri, and between them, they decided to try out this new technique. But since they didn't have a balloon facility, they trekked to Tiger Hill, which is near Darjeeling, and to Sandakphu, which is also close by, to expose photographic plates to cosmic rays, so in the lower reaches of the Himalayas. So here is a Google map. You see Darjeeling here. Darjeeling is here. Tiger Hill is here. And you have to go all the way to Sandakphu. There were no roads at that time. So you had to go on muleback or horseback and put the plates there, expose them for 15 days, then again go and pick them up and so on. Real adventurous hard work. Well, this is what they did. In those days, you could get these packets of plates, and plates really meant glass plates. Ilford was the famous company which provided these plates, and this is what they look like. You've got a box of those plates, and you had these actual glass plates which were coated on one side with an emulsion containing the silver halide. And therefore, you took a box camera, you opened the front, you pushed the plate in at the back, and then you took photographs from that. However, what these people did was, instead of that, they stacked the plates together like this, and they waited for cosmic rays to come from the top and pass through them and leave certain marks in them, which then they would later study under a microscope and try to find out the tracks and see what was happening. So here we see one early paper by these people saying photographic plates as decays of mesotron showers. So mesotron was the name for the meson in those days, and it is the pion which they were looking for. So in the early days, this is one of their first papers, and you see here that it is signed D.M. Bose and Bhabha Chaudhuri, and the first citation is to Blau and Wambacher, also to both. Now, there's a rumor which goes around that Bose and Chaudhuri discovered the pion. Did they really do that? let's try to address that question. Now, during this war, they had access only to what were called half-tone plates. That is, plates which are coated on one side. Plates which are coated on both sides gave you much better resolution, but these were reserved only for the war work, for the reconnaissance work from high-flying aeroplanes, and they were not available to civilians, not even to English civilians, forget people who were regarded as natives in those days. So they could not get hands on it. And I'll show you how the difference matters. Here is a grainy and sort of low resolution picture taken with a half-tone plate. This is the Howrah station as it was in those days. Contrast it with a modern picture. You can see that so much more detail, so much more precision comes. But working with that, you see here that the mesotron masses measured by them using the grain spacing and the length of the track, they varied over a large range. So I've just picked up this last column. This is mass of the electron. So it varies from 88.4 MeV, so 76 MeV and so on. The actual mesotron mass they got was about 82 plus minus 21. So large margin of error. And mostly results below 100 MeV. The muon mass is 105 MeV. The pion is even heavier, 139 MeV. So one track here, one result here is similar to the pion mass. And a lot of people have jumped on this and said, look, they saw a pion. But of course, then we should also say that they saw something of mass 76 GeV, which doesn't exist. So it's probably that these are just within the experimental error, and what they saw were all muons. And I'll explain the reason for that also. The actual pion was discovered by these four gentlemen, by Powell, who was the leader of the group, and his assistants Occhialini, Method, and Lattice. So what happened was that after the war, the British government, spurred by Patrick Blackett, they asked the plate manufacturers to produce improved high-density plates. Why? Because they wanted to do reconnaissance over Russia and see whether Russia was building nuclear weapons. Now, because Powell had worked for the government during the war, he had easy access to these plates. And then Lattice came up with the suggestion that he should put some more boron in the emulsion. Now, this worked like magic and is described very poetically by Powell in his Nobel lecture. He says it was as if suddenly they had broken into a walled orchard, which protected trees had flourished, and all kinds of exotic fruits had ripened in great profusion. And the first low-hanging fruit they found was the pion. And these are actually the graphs from their pion discovery paper. And you see here that the first decay that happened, this short track is the pion. This long track is the muon. This track which I have included here is invisible. That's the neutrino. And then the muon comes here and decays into an electron and two invisible neutrinos. The electron track is there. It happens in every case. So you see the long track you see here is the muon. And the short track is the pion. So with the kind of resolution which Bose and Chaudhuri had, they could not have seen these short tracks. So it's unlikely that they discovered a pion. Of course, everything is probabilistic. Once in a while, a pion could leave a long track, but the chance is less. Anyway, the 1947 Powell certainly proved the existence of two mesons, and this had also been suggested by the Japanese during the war, but the work didn't go anywhere because of the war. The journals didn't come out of Japan. Well, Powell got the Nobel Prize in 1950. Occhialini returned to Italy. He won the Wolf Prize in 1979. Cesar Lattice became the leader of cosmic ray research. Hugh Moorhead went on to work on parity violation. He wrote a famous textbook, which was much read in the earlier generation. Marietta Blau never got a regular paid position, and she died of cancer in 1970, contracted while studying nuclear emulsions. Herta Bombacher, it was even worse. She had become a Nazi during the war. She was imprisoned by the Russians, and when it was clear that she was dying of cancer, they released her and to come home, and she died of cancer in 1950. No recognition at all, and the work of Bose and Chaudhuri is completely unrecognized except by historians of science and Indians. Well, let's come back to Bombay, and I take you to Wilson College near Chowpatty, and here there was a gentleman called H.J. Taylor, who was a student of Rutherford, who was actually working in Wilson College, and he was also using plates, but to study nuclear physics, to study alpha particle tracks. There was also Vikram Sarabhai, who had come back to Bangalore and was offered an assistantship by C.V. Raman. And though he was interested in cosmic rays, he did not attach him to Homi Bhabha, was already a famous figure, but he preferred to work on his own. And he wrote 6 papers during the war period from Bangalore, all single author papers. And he was more interested in the latitude effect and so on of cosmic rays. Here is another paper by Sarabhai. But he went back to Cambridge after the war, won his PhD there, came back to India, collected money from his rich friends like Bhabha to found the PRL at Ahmedabad at the age of 28. But he didn't become the director. K.R. Ramanathan, who was an experienced person, became the director, and Sarabhai took over director much later at 65. And he was a simple professor in PRL. He trained many PhD students, among whom was the late U.R. Rao. Here is a picture of Dr. U.R. Rao when he was young. He passed away quite a few years back. And Sarabhai was a very simple person. He worked immensely hard. In fact, he worked so hard that he died at the very young age of 52. But Sarabhai's interest moved from cosmic rays to anti-magnetic fields, from there to solar physics, from solar physics to satellite-based observations. And therefore, he realized that we need to launch satellites. So this made him the father of India's space program. You see him here with another cult figure. This is the late Abdul Kalam, of course, who went on to do many other things. And finally, the fact that today we can launch our GSLV and PSLV is entirely due to Sarabhai's interest in cosmic rays. Well, let me now come to the cosmic ray group at TIFR in the 1950s. And of course, Homi Bhabha was the leader. He had founded the group. He gave it its initial direction. I've described some of his work here. After 1954, he was mostly involved in setting up the Atomic Energy Establishment, the Atomic Energy Commission. He was internationally committed to the International Atomic Energy Agency and so on, and peaceful use of atomic energy. He wasn't doing too much particle physics, except as a sort of overall supervisor, overall friend, philosopher, guide to the others. So who were these others? They were like a Navratna, and the most important of them at that time was Bernard Peters, who was born Bernard Petrovsky. He was a Polish scientist. He had come from Posen, and then he had worked on the Manhattan Project. So he had a long history of escaping from oppression and so on. And even after the war, he was persecuted as a communist sympathizer, being Oppenheimer's student. So Bhabha invited him to come and join TIFR, and he did come and stayed there for 8 years. So in 1959, he moved to the Niels Bohr Institute at Copenhagen. He later became director of the Danish-Spanish Space Research Program. Now, realizing that cosmic rays provide very high energies, more than you could get in terrestrial sources, Peters focused on the possibility that these could contain the showers could contain exotic particles created by the intense energy. So his team at TIFR looked for antimatter first, and then for exotic transuranic nuclei. Of course, today you produce transuranic nuclei because you have much more flux and high energy colliders and also nuclear reactors. However, with the low flux of cosmic rays, the instruments were simply too small to catch antimatter, but they did find some heavy nuclei, and that became the focus of some of his research. Also, his student worked on that. M.G.K. Menon had come to Bangalore. From Bangalore, he went to Bristol. He worked with Powell for his PhD. He did very significant work on K-meson decays, and in 1954, though he had many offers from around the world, he came and joined TIFR. He threw himself with enthusiasm into the balloon flights and emulsion projects. He also aided Bhabha in administrative matters. So in 1966, he became director of TIFR when Dr. Bhabha was unfortunately died so young. And then he continued Dr. Bhabha's good work, of course, in developing TIFR. We know that. And during his career, he held almost every important position in science, Secretary DST, and various things, including he became a Minister of Science for a short time, which is not what every scientist does. Now, his Bristol work will be remembered for the observation that K-mesons can decay into 2-pion or 3-pion final states. And he was also the leader of the Polar experiment and the spokesperson for that in the international forums. Bhabha Chaudhuri, whom we have already met, she had gone to work with Patrick Blackett at Manchester after the work with William Bose, and she completed her PhD there. She got her degree in 1952, but she had already joined TIFR in 1949. She spent 8 years, like Peters, in the cosmic ray group, and then she moved to the PRL. She remained there till 1957. Then she took a voluntary retirement and went back to Kolkata, and she was a guest scientist at the Shah Institute till her death in 1991. So I should mention that Bhabha Chaudhuri was very different about publishing papers, As a result, many of her contributions went unrecorded and her name was almost forgotten. But recently, her reputation has been resurrected as an icon of the women in science movement. She was one of the very first women who did such important work. And in fact, even a star has been named after her. Though belated, this recognition is very well deserved. And I am proud to say that I was one of the first people who, in the talk I gave at the Calcutta University Centenary celebrations in 2014, was one of the first to highlight her contributions to particle physics. Anyway, at TIFR, she built the cloud chamber experiment, and she was deeply involved in the Kolar Gold experiments also. And in fact, she had a plan to develop a cosmic ray station at Mount Abu from PRL, and that was actually very much favored by Dr. Sarabhai. But when Sarabhai suddenly passed away, this thing didn't happen, and then I think that was one of the reasons why she decided to move away to. There was Roy Daniel, Ranjan Roy Daniel. Nadar is his full name, but he was known as Roy Daniel. And he joined Bhabha as a research associate, stayed here for his life, and taught to become senior professor dean of physics. He later became chairman of the advisory committee for ISRO and also scientific secretary of the COSTED. And then after retiring, he moved back to Nagarkar. He was a true leader. He is known to have trained and encouraged many young scientists who were then discouraged by the earlier failures of the program, and he just kept them in science. So he had a very important role in a very quiet and unstated way. So he is credited with discovering electron primaries in cosmic rays, still a topic of intense research. He also pioneered the fields of gamma ray astronomy and far-red astronomy in India. We have those things in TIFR today. And he was by the way, he was also an early advocate of the study of climate and environmental change due to human activity, and he used his international to further these studies in India. Sukumar Biswas, he did one PhD with Meghnad Saha at the Institute of Nuclear Physics, now the Shah Institute of Nuclear Physics. He then went to Melbourne and did a second PhD with Bernard Hopper, and this PhD work centered on the discovery of the lambda barrier. I'll come back to the moment. In 1952, he joined TIFR and worked in the field of emulsions and cosmic ray tracks. From 1959, he got interested in solar physics and became an associate of NASA. He retired in 1989 and settled in Bombay. He wrote a very influential textbook called Cosmic Perspectives in Space Physics. It's still one of the reference books for this subject. And he is the only Indian who can be credited with having discovered a new particle, which was the lambda barrier. In TIFR, his emulsion work gave a new method for measuring K-meson masses. And then as he moved towards solar physics, he pioneered the understanding of solar flares and their composition. He later used the Skylab data to discover what are called anomalous cosmic rays. He was also involved with the Anuradha satellite, so another luminary. Then people who did their PhDs here. V.V. Srikantan, who later became director of TIFR. He originally had joined the ISC, but Bhabha sort of persuaded him to come to TIFR to work on cosmic rays. He did his PhD, in fact, with Bhabha, then went to work with Bruno Rossi, came back to TIFR, later became the director, and then joined the NIAS Bangalore, remained there till his death last year. So Srikantan was also a member of the Atomic Energy Commission and Planning Commission. He quietly played an important role in the furtherance of mega science projects in India. Other people will know more about it than I do, but I believe his role was very encouraging and important. He was an experimentalist par excellence. Srikantan will be remembered as the pioneer of the Kolar experiments, which I will talk about more. He was also deeply involved in the proton decay experiment at Kolar. Devendra Lal, who came from Varanasi, graduated from BHU, and he did his PhD with Bernard Peters and also worked with H.J. Taylor, who was in Wilson College, which I told you. And he worked on cosmic rays and the radionuclides. So he continued the work he had been done with Peters. Later, he moved to PRL as its director. And in 1987, he went to the US. He moved to the Scripps Institute of Oceanography at San Diego. And that's where he died in 2012. His interest in radionuclides formed by cosmic rays led him into the field of geosciences, and he was also a pioneer of radiochemistry in India. He established the National Radiocarbon Laboratory at TIFR, the first place which did radiocarbon dating in India. His best-known work was his compendium with Bernard Peters on the rates of the formation of radionuclides in rocks as a result of cosmic ray bombardment. This was a reference work until quite recently, and the importance in geological studies, of course, cannot be, because you can date rocks and tell the antiquity of rock formations from there. And his radiocarbon dating facility was invaluable in establishing the antiquity of Indian culture, particularly the Harappan civilization, which was. Lots of other evidences were there, but here was solid scientific evidence that it was indeed as old as people thought it was. Finally, Yashpal, you see him here as a young man. He had studied at Lahore and then at Delhi, and through the chaos following partition, his studies had got interrupted and so on. But he came to TFR and worked for some time. Then he went to MIT, did his PhD with Bruno Rossi, returned to TFR in 1958 and remained till 1983. In 1972, while he was still a member of TFR, he became director of the new Satellite Accessories Center at Ahmedabad. And then he held various things, but the most important thing he's remembered for was as UDC chairman, where he pioneered these inter-university centers, the IUSC, the IUCA, and so on. And of course, posterity will probably remember Professor Yashpal, not as the young man I showed you, but as the avuncular figure who used to conduct Turning Point. And I think he was able to inspire many young Indians to take up science as a profession. Yashpal's main scientific work was in identifying unusual astrophysical sources for extrasolar cosmic rays, showing how showers of light nuclei remain trapped in the solar system, and so on. As an educationist, he advocated a lesser burden and more fun in learning science, which he led from the front. He was also an advocate of teacher training. And it's interesting that some of these ideas are now enshrined in the national education policy. So he was a person who did look forward to the future. Here are some of the early PhDs done from TFR list. I'm not going to go through all of them, but you see Srikantan here, and you see Devendralal here, and others, of course. Now, I should also mention that for the theoretical work, there were many particles discovered in the 50s after the lambda, except for the lambda, which was not discovered here. Also interesting ideas like the Young-Mills theory, the intermediate vector boson hypothesis, and so on. But none of these were done in India. The TFR group, in particular in Indian cosmic ray research, was nowhere involved in these momentous developments. One of the reasons was that Bernard Peters had diverted much of the work to the production of exotic nuclei, which is important, but it's more useful in geophysics, not in the field of particle physics per se. And TFR, though there were many bright people, it lacked another theorist whose caliber was like Bhabha's, and he was simply too busy. And S.N. Bose and Meghnad Saha, brilliant scientists, were all past 60. D.S. Kothari was then advising the Defense Ministry, so there was nobody to really take up the lead after Bhabha had sort of. That's one thing in which India did do things, and I know I'm beyond my time, so I'll just go through this quickly, was in the Kolar experiments. So Kolar, you see a bigger version of the map. So the Robertson Pit here, the Kolar gold fields. And here there was the Champion Reef mine set up in 1900, a gold mine, of course. And this was where the experiments were conducted. So it goes very deep. So as early as 1948, Bhabha sent Srikantan to Kolar together with Narayanan and Ramanamurthy to go and measure the cosmic ray neon flux, which actually goes down like this. So the Kolar mines are somewhere here on this graph. No mine goes this deep nowadays. So the flux initially declined as it expected, but then suddenly began to rise. And it was Bhabha who guessed that this was due to some radioactivity in the rocks there. And when you go down further, it disappears. In fact, there is some thorium-232 which was discovered there. Now, at a depth of 2.7 kilometers, the cosmic ray neons were completely shielded. This means that if there was nothing in the surrounding rocks, you would see nothing. But Markov, in 1957, realized that neutrinos can easily penetrate to such depths, and if they form muons by inverse beta decay, you can see those muons. So if you are seeing muons at this depth of 2.7 kilometers or more, what you are really seeing are neutrinos. So the TFR group took up this suggestion with enthusiasm, and Kolar was the ideal setting to measure this. We see V.S. Narasimhan, who was the leader of this program at that time. And here is the very first paper published in 1965, the first observation of what we call muon atmospheric neutrinos. And you see the authors, you see Menon, Narasimhan, Ramanamurthy, Srikantan, and so on, with the other foreign collaborators. And here was a rival paper brought out by no other than Frederick Reines, the discoverer of the neutrino, Nobel laureate later. But their paper came on 26th July, and this paper was on 12th July. So the TFR group beat them to it as the first observers of atmospheric neutrinos. By the 1970s, the Kolar experiment was revamped to look for proton decay, but unfortunately no events were found. The proton seems to be stable. From 1975 onwards, some weakly interacting particles of mass around a few GeV seem to have passed through the Kolar detectors. There's a suggestion that they could be dark matter, Perhaps if dark matter is discovered, one day we will realize that those were the first dark matter events. It remains a matter of speculation. However, the Kolar experiment terminated in 1992. The Kolar goldfields were shut down in 2001. And if you go there today, you will see a picture of decay and dissolution. So I will actually skip this part about Aladi because of lack of time and also about its gill. And I will now just come to the last part of that. In the 1970s, there were only a few places in India where energy physics or particle physics was being done. Of course, Bombay with TFR and BRC was one of them. PRL was the other, but there were a few others. But in that year, in that period, some new institutes were found. IIT Kanpur started a group. The Banaras Hindu University started a group. P.N. Pradhan founded the IOP. The University of Hyderabad started a group. N. Mukunda started particle physics at the IISc. And then the first DE Energy Physics Symposium was held at the IIT Bombay in 1972. During the 1980s, there were no new things which came up, but the first SERC, Theoretical Energy Physics, was held at the ISC in 1985. The first string theory school was held at IIT Kanpur in 1986. And the first workshop on high energy physics phenomenology was held at TFR in 1989. During the 90s, two new institutions which particle physics groups exist came up. One was the Harishchandra Research Institute, part of our DA family, part of HBNI, and also IIT Guwahati. The first experimental SERC school was held at TFR in 1995. So between 2000 to 2020, last 2 decades, we have seen that now there was the growth of so many new institutions where particle physics groups have come out. And the last and latest, so you can see the one where people are doing particle physics now. And the last, and perhaps one day it will be the greatest, is the INO project at Madurai. And we hope it will. Now, there are many other places in India where I expect that in the next 20 years, we will also see our particle physics grow. And so my hope is that the picture in 2040 will be more like this. But that remains to be seen. It's a fervent hope, and I expect it to be like that. Now, it's time to end this long talk. So I'll end with a comment about these pioneers of science in India. I want to point out that they were like David facing Goliath. They were fearless, energetic, and confident. They tackled cutting-edge problems without fear of failure or ridicule. They were often wrong, but this did not deter them from coming up with fresh ideas. They had that courage. They were willing to tackle the most difficult of problems with the minimum of equipment and sometimes money out of their own pockets, especially in the early days. They had huge ambitions and they worked tirelessly to see them fulfilled. Sometimes it was fulfilled, sometimes it was not, but they worked on it whole time. And perhaps the most important lesson to draw from their story is this: the fact that they had this courage and conviction and enormous effort. So with that, let me thank all these pioneers on behalf of our present day generation, and let me thank everyone, all of you who have heard this talk and have stayed with me with so much patience. Thank you.
Thank you, Professor Raychaudhuri, for a very fascinating journey through the development of particle physics, starting from the late 19th century, and particularly highlighting not only Dr. Homi Bhabha's contributions, but the contributions of many other Indian scientists who were relatively unknown. It was a highly appropriate talk for this occasion today, because we need to remember Dr. Bhabha for many reasons, as you mentioned, not only the important contribution which he made for the nuclear energy development, but also how great a scientist he was. If the younger generation realizes, the inspiration will be even higher. So, and we thank you very much for your excellent lecture. Considering the occasion, probably we will not go into a long question answer session, but perhaps a few comments or observations can be welcome.
Sure.
Professor Gautam Bhattacharya would like to add anything or mention anything?
Well, I mean, nothing much. I have heard part of the talk before, and I was spellbound. I was listening to his talk as always. So nothing much to add. Except that, I mean, I don't know whether Professor Nobo Mondal is listening to this talk. He told me a story. I don't know whether it's an inside story that IYNS was trying to access the Kolar gold mine site without approval of the government and of TIFR authority. Immediately after the, this observation was, kind of came to limelight. But eventually, somebody had to intervene. I don't know whether it was Bhabha or no, it was much after Bhabha probably. Maybe Srikantan, I don't know. But IYNS was probably not allowed or something happened. I mean,
Yes, I think I know a little bit of that. Originally, the proposal was that IYNS would be part of this collaboration, but IYNS wanted to lead the collaboration, and he wanted basically to take all the credit if it came. So at that time, I think it was so Bhabha was still around, and Bhabha had actually said that we can't just give you this Kola goldfish to do your own experiment. We will do our own experiment. So it actually started like that, and then IYNS went to South Africa and did this experiment. So I would say it was an act of great courage. I would say it was an act of great courage because IYNS was already famous as the discoverer of the neutrino. And Bhabha basically told him to go about his business.
That's right. He probably didn't get Nobel Prize his Nobel Prize was much later, of course. Much later. But I mean, he was already known to be a big shot at that time. And Bhabha, showed him the boots. I mean,
Absolutely. Sorry, fine.
If Professor Mustansir Burma would like to make any observation?
No, I don't have anything much to add. Like Gautam, I would say I really enjoyed the lecture, especially, learning about other contributions to high energy physics from India, which I was not so well aware of. Dr. Bhabha's achievements I knew something about, but I really enjoyed the historical perspective, and I thank HBNI for hosting this, and I thank Sreerup, of course, for the talk. Thank you.
Thank you, sir.
So thank you, Professor Sreerup Raychaudhuri, once again for your fascinating talk. And it is, of course, going to be thanks to you also for agreeing to provide us the presentation to be put up on our website. For all the viewers, including those who missed it, if they want to see the PowerPoint present or the PDF form of the presentation, it will be available in our website, anuvidya.in, maybe later from evening today or tomorrow. And of course, this will also be available on the YouTube for those who want to view it later. So I'm sure this will be very enjoyable for many more people to come, not just those who joined the meeting today, but I'm sure it will benefit a very large number of viewers. Thank you once again, Professor Raychaudhuri.
Thank you, sir, for inviting me. Thank you very much.
Okay, now we close the meeting. And thanks once again to all the people who have joined both through WebEx and through YouTube. And thanks also to the Indian Youth Nuclear Society for joining with us to record this. I'm sure through the IYNS, this will reach much larger, younger population of the nuclear scientists across the world. Thank you very much to all of you.